Morning and welcome to our lesson today. Now, just to help you recap, last time we looked at vertical projection, and we managed to come up with about 3 different equations. Only that we limited ourselves to 2 directions. Now, when we project the body upwards, G is negative. Remember that we said during a vertical projection, only G acts on a body, and G is the gravitational acceleration. And when we are moving upwards, the influence of gravity on a body is actually negated. Now, our equations became U minus GT for the upward movement. That was our first equation. Our second was talking about H, which we found to be UT minus a half GT squared. And number 3, we looked at another one which related the final velocity to the initial velocity and also to the gravitational acceleration as well as the vertical height. Now, how about downward movement? For downward movement, we found out that G was very positive, and therefore our equations of vertical projection will now change to 1. V is equal to U plus GT plus, because we are moving in the direction of action of gravitational force. Number 2 is an equation that should express height as a factor of initial velocity, time, as well as an aspect of gravitational acceleration. And equally, 3 gives us velocity final as a factor of initial velocity and as well as gravitational acceleration and height. Now, today we want to limit ourselves to upward movement, and we will use our 3 equations to get an expression for 3 or 4 important aspects of vertical upward projection. And we want to talk about time of flight. We want to talk about maximum height. We want to talk about final velocity, and also we shall consider what we call the time to reach maximum height. We shall consider the 4 using our equations of vertical projection in upward direction. We want to look at those 4 Probably we can rewrite our equations here. We are moving in the upward direction, and therefore we negate G. Then our second equation will be H, which is equal to UT minus a half GT squared. Number 3 is V squared, which is given by U squared plus 2GH. Now, let us start by the first one, which is the time to reach maximum height. The time to reach maximum height. And it is worth noting that at maximum height, final velocity reduces to 0. That when we want to claim that our body that we have projected upwards has reached maximum height, it means that the body will attain 0 velocity. And therefore, we would like to use the first equation of upward projection. We want to use the first equation of upward projection to come up with an expression that we can use to calculate time to reach the maximum height. And according to our list there, the first equation, V is equal to U minus GT, is our first equation, which I want to call star. But here at the maximum height, V has reduced to 0. Therefore, we want to substitute the value of V in equation star, so that we have 0 being equal to U minus GT, and this implies that U is actually equal to GT. And now that we are interested in T, we can divide both sides by G to make T the subject of the formula. And what we end up with is an expression of T in terms of U and G, and we can write it as T is equal to U over G. Now, if you have this equation, it can lead you to time to get that. You remember, at maximum height, final velocity reduces to 0. Again, G is also negative because we are moving in a direction opposite to that of action of the gravity. Therefore, we applied the first equation of upward projection, which states that final velocity is equal to initial velocity minus the product of gravitational acceleration, and you multiply by time. Now, Taking into consideration the fact that V at maximum height is 0, we can be able to substitute that in our equation star so that we end up with something like this. And we can therefore make T the subject of the formula to come up with that expression. How about the time of flight? Time of flight. And it's good to remember that the time of flight is basically the time taken for a body to get back to its point of projection. Time taken for a body to get back to its point of projection. That is to mean if a body starts from a point A, somewhere on the ground, it moves upward to a height that we are calling maximum height, and back to where it was projected from. The time taken to go to the maximum height and back is what we are interested in this case. Now, we are considering the distance covered by the body. We are considering the distance covered by the body, which we are going to call the displacement. And the displacement is a vector. Therefore, if we talk about maximum height being positive, getting back to the point of projection is actually negative. Maximum height. Now, if we take our maximum height and we add to the negative of the maximum height, we get a 0. Therefore, at the point of projection, the displacement is actually 0. Very important, the displacement is 0. Now, let us consider the second equation. Consider the second equation. H is equal to UT minus a half GT squared. We can call it equation 1. Then we can multiply equation 1 by 2, so that now twice the maximum height is going to be given by 2UT minus GT squared. But remember, H is 0, and therefore, if H is 0, and we substitute, let us call it this one equation 2. We substitute H in 2, we are going to get 0 being equal to 2UT minus GT squared. we can factor out t, so that now 0 becomes t into ut minus into u minus gt. Now here we can have some two results. A is where we can take t to be 0, and B is where we can take 2u minus gt to be equal to 0. Therefore, 2u is equal to gt, and t will be equal to 2u over g. Now, if we consider the first case where our t is 0, and now we look at what we are talking about, the vertical projection. Scientifically, a body cannot take 0 time to go to the maximum height and back. Therefore, that one is outlawed, and the only one that we are left with is t equal to twice the initial velocity divided by gravitational acceleration. We would also like to have an expression for the maximum height. Maximum height which we are calling h maximum, and it is the highest point from the ground reached by a projectile. The highest point from the ground reached by a projectile. And recall at maximum height, v is 0. The final velocity at maximum height is 0. So we consider the third equation. And our third equation, v squared is equivalent to u squared minus 2 g h but v is 0 at maximum height. Therefore, that leaves us with our third equation changing to 0 is equal to the initial velocity minus twice gravitational acceleration and multiplied by the maximum height. Now we make h the subject. Make h the subject of the formula, and this implies that u squared will be equal to 2 g h, and we can divide both sides by 2g so that we are left with our h being equal to u squared over 2g, which is the maximum height that we are interested in. Therefore, we will use the third equation, and remember to substitute for v with a 0, now that at maximum height, velocity final reduces to 0. Now, the fourth aspect of vertical projection that we want to look at is the final velocity. Final velocity v. Final velocity v, or the velocity at the point of projection. Now here we want to consider a projectile that has gone to its maximum height from the ground and back. And now the question we have at hand is the velocity with which it hits back to its point of projection after reaching the maximum height. After reaching the maximum height, and we remember that at the point of projection back from the maximum height, the total displacement is 0. Now, using the third equation, we want to use the third equation. V is equal to u squared minus twice the product of gravitational acceleration and the maximum height. But we are saying that at this point, h is going to be 0. Therefore, if we substitute, we get our v squared being equal to u squared. Then we can consider getting the square roots both sides so that v should be equal to positive or negative u. But again, u is positive when the body is moving upwards, and when the body is coming back to its point of projection, we are moving against the initial velocity, and therefore we take v to be negative u. We take v to be negative u. We have been able to come up with 4 expressions. 4 expressions that we are going to use in our next examples to find out whether we can be able to calculate the aspects we have been looking at. Example number 1. A boy shot a ball vertically upwards with an initial velocity of 20 meters per second, and we are given our gravitational acceleration as 10 meters per second squared. Then the question requires us to get, number 1, the maximum height reached. And from what we have derived, our maximum height is given by u squared over 2g, and we have been given u as 20 meters per second, so we square that, then we divide by 2 times our gravitational acceleration, which is 10 meters per second squared. And this one is going to give us 400 divided by 20. Remember, we're talking about the height, so the units will change to meters, and this gives us 20 meters as the maximum height reached. Now number 2, or part 2 of the question, we want to get the time to reach maximum height. Time to reach the maximum height, which is given by 2u over g. Again, we have been given u as 20, so the product of 2 divided by 20, and this we divide by 10, which is going to give us 4 seconds. The third part requires us to get the time of flight. Which is the time taken to reach the maximum height and back, which will be given by t is equal to u over g, which will be given by 20 divided by 10, giving us 2 seconds. Then part 3 is the time of flight, which is given by 2u divided by g. that is twice the initial velocity. You divide by the gravitational acceleration, and this is going to give us 4 seconds. Therefore, we can note that time of flight is equal to twice the time to reach maximum height. And finally, part 4, we can look at part 4, which is the velocity. Velocity with which the body hits its point of projection. Which is going to be v, and is given by negative of u. And now that our u is 20 meters per second, then v is negative 20 meters per second. 20 meters per second. 20 meters per second. We can look at another example. A stone is projected vertically upwards. With an initial velocity from the ground. A stone is projected vertically upwards with an initial velocity of 30 meters per second from the ground. Now, using g as 10 meters per second, the question requires us to get the time taken to reach the maximum height. Now, and we know that t is equal to u over g. Our u is 30 meters per second, and our g is 10 meters per second squared. Therefore, our t will be 3 seconds. Number 2, or part 2 of the question, is the time of flight. Time of flight, and we are noting here that time of flight t is twice the time to reach the maximum height. Therefore, t will be equal to twice the time to reach the maximum height, and you get 6 seconds is the maximum height reached, and which is given by u squared over 2g. Our u is 30, so 30 times 30, and we divide this by the product of 2, and the gravitational acceleration, which will yield 45 meters. 45 meters. Let's look at the last example, last one. The last example. That a ball is thrown upwards with an initial velocity of 10 meters per second. It hits the ceiling 5 meters high and bounces back. We want to get the time. Number one, the time taken to reach the ceiling. The ceiling. T, in this case, our ceiling is the maximum height achieved by the ball, and that will be given by u over g, which is 10 meters per second divided by 10 meters per second squared, and we are going to get just 1 second. Now, part 2 requires us to determine whether the ceiling would actually be the maximum height that the ball would have achieved. So let us assume that we had no ceiling and determine the maximum height that the ball would have risen to. And this one is given by u squared over 2g, which is 10 squared and we divide by 20, which gives us 5 meters. That would be the highest point that the ball would have risen to. So the question is, we have our ceiling 5 meters above the ground, and supposing we didn't have a ceiling, the ball that was thrown up with an initial velocity of 10 meters per second would have gone to 5 meters before the velocity reduces to 0. So yes, that would be the maximum height. Can I go to something else? Now we look at horizontal projection. Now, horizontal projection is a situation where a body is given an initial velocity in the horizontal direction. Now, this is where a body is given an initial velocity in the horizontal direction from some point above the ground. A body is given some initial velocity in the horizontal direction from some point above the ground. Now, there are a few things that you should take note of here. Number one, for this body that has been given an initial velocity in the horizontal direction from a point on the ground, now the initial velocity in the vertical direction is actually 0. That the initial velocity in the vertical direction is 0. Number two, second point that you should note is that number one, you in the vertical direction is actually 0. Number two is that the body undergoes vertical acceleration equal to g. Vertical acceleration equal to g. Number three is that the horizontal acceleration A is actually equal to 0. Therefore, even as the body covers the vertical, the horizontal distance that it should cover, it also moves vertically or experiences free fall due to gravity. Therefore, the body describes a curve, say from a point A. Let us take this distance to be h. Now, even as it moves horizontally, it also accelerates downwards because of gravity, and therefore the trajectory is going to be a curve. Now, clearly, even as the body falls, it also covers some distance horizontally. So it covers two distances at a time. The horizontal distance is covered at a uniform speed u, which is the first or the initial velocity that we gave it in the horizontal direction. And this u is constant. Now, given that no external forces are acting in the horizontal direction on the body, therefore u is supposed to be uniform throughout the motion, and that is why we are taking the acceleration in the horizontal direction to be 0. However, u in the vertical direction, as the body will experience free fall, in the vertical direction u is 0, although we have g as our acceleration, which will propel the body towards the ground. Now, this horizontal distance covered, the horizontal distance covered is called the range. It's actually called the range, while the vertical distance is actually our height. And again, u only acts in the horizontal direction, and u in the vertical direction is 0. Now, let us apply our equations of motion to get an expression for the range. Now, we use the second equation of linear motion. S is equal to ut plus a half at squared. Our S in our case now becomes the range, so we can use capital R. But acceleration in the horizontal direction is 0. Therefore, we can substitute that so that our range becomes ut plus a half our acceleration is 0 and the time taken is t, and our 0 acceleration reduces this term to 0, and our range is therefore given by ut is the product of the initial velocity and the time taken and the time taken. How about the vertical? How about the vertical height? Now that we are in agreement that the body covers two distances at the same time, we still use the second equation, only that this time height will be given by ut plus a half gt, where g is our acceleration due to gravity, and we are using positive because we are moving downwards. But we can recall that u in the horizontal, in the vertical direction is 0. U in the vertical direction is 0, and we can still substitute for u in our equation so that this one is squared, so that now the first term reduces to 0 and our height is given by a half gt squared, half the product of the square of time and gravitational acceleration. A hammer is thrown horizontally from the roof of a building with an initial velocity of 10 meters per second. We are supposed to take g as 10 meters per second square and determine the height of the roof. The height of the roof is the vertical height, which is given by a half gt squared, and hits the ground below. After 3 seconds. You're supposed to get the height of the roof, and the height is given by a half gt squared, where g is our gravitational acceleration and t is the time taken. Therefore, we can substitute a half multiplied by 10 and then by the square of our time, which is 3 squared, and we can get, is it 45? 9 times 5, 45 meters. Part 2 is the distance from the foot of the building where it lands. On the ground. The distance from the foot of the building where it lands on the ground, and the horizontal distance covered is what we call the range, symbolized capital R, and the range is given by the product of the initial velocity and the time taken, which is going to be 10 times 3. And this gives us 30 meters. 30 meters. We can look at one more example. The question reads that an arrow is shot horizontally from the top of a cliff and lands on the ground 100 meters from the foot of the cliff. We are required to assume that air resistance is negligible and then determine the initial velocity as well as the height. We have been given the range as 100 meters, that is the horizontal distance that has been covered. Then the time is 4 seconds. Then gravitational acceleration is 10 newtons per kg or 10 meters per second squared. So number 1, you are required to get the initial velocity. Initial velocity. And the initial velocity from the equation of the range, the product of the initial velocity and the time taken gives us the range. In our case here, we have been given the range as 100, so we take it to be the product of the initial velocity which we want to look for, and the time, which is 4 seconds. And we can divide by 4 both sides, so that now our initial velocity is 25 meters per second. Now, we also want to get the height of the cliff. It is given by a half gt squared, and we substitute for g as 10, and we multiply this by the square of time, which is 16, and is supposed to give us the height as 80 meters. 80. That's all for today. In the next lesson, we look at motion graphs. Thank you.